Hello, and welcome to the Sentinel Innovation and Methods Seminar Series. My name is Rishi Desai. I'm an assistant professor in the Division of Pharmacoepidemiology at the Brigham and Women's Hospital and Harvard Medical School, and I will be moderating the session today. The US Food and Drug Administration Sentinel system helps address questions related to the safety and effectiveness of medications. The Sentinel Innovation Center focuses on developing innovative methods to further advance Sentinel by leveraging new data sources, bringing new tools, and enhancing real-world evidence capabilities through advanced analytics. Sentinel Operations Centers focuses on supporting the FDA in the use of Sentinel Common Data Model and associated modular programs or tools to gather evidence to support regulatory decision-making. We launched this webinar series to engage experts and innovators in key areas related to Innovation Center's master plan and Operations Center's methods work. With that, I'm pleased to introduce today's speaker, Dr. Shu Shi. Dr. Shi is an assistant professor in the Department of Biostatistics at the University of Michigan. Her research focuses on developing novel statistical methods that provide insights from high volume and high variability administrative healthcare data, such as the electronic health records. She develops scalable and automated pipelines for curation and harmonization of EHR data across healthcare systems. She also develops causal inference methods that harness the full potential of EHR data to address comparative effectiveness and safety questions. The title of this presentation is an introduction to negative control and proximal causal learning. Before we get started, I would like to mention that your lines are muted. If you'd like to ask a question, please type them into Zoom question and answer session. We will answer the questions at the end of the session. Finally, this session is being recorded and will be made available through the Sentinel webpage, which can be found at sentinelinitiative.org. Without further ado, I will hand it over to Dr. Shi and thank her for joining us today.
Thank you so much, Rishi, for your introduction. So hello, everyone. Thank you for coming here. And I really appreciate this opportunity to talk about some of our recent work on controlling for unmeasured confounding, leveraging a new type of variable called negative control variables, or AKA proxy variables. So before going into details, I'd like to acknowledge that the methods that I'm going to talk about are teamwork by a group of crazy smart people, and I'm really fortunate to work with them as a team. Okay, so let me start with a typical scenario in causal inference. In an observational study, we're typically interested in estimating the causal effect of treatment, typically binary, denoted as A, on some outcome denoted as Y. To define the potential outcome, to define the causal effect, we introduced the potential outcome framework, where for every individual, there are two outcomes. One is the potential outcome had the individual been given treatment, Y1, and the other one is the outcome had the patient or individual being given control, Y0. And a commonly seen causal estimate is the average treatment effect, ATE, which is the mean difference between Y1 and Y0. Now, consider a randomized clinical trial where treatment is randomized. In that case, in the treated arm, the people in the treated arm would be a random sample of the target population. So if I take the mean outcome among the treated group, that would give me the mean of Y1. And similarly, I can use the mean outcome in the control group to estimate mean of Y0. However, in the observational study, there are many factors that are associated with both treatment decision and patient's outcome. For example, age, gender, and health status. So I'm going to use letter X to denote the measured confounders. In an observational study, to identify the mean difference between the two potential outcomes, we typically make a key assumption, which is called Noaa measured confounding. It says that if I am able to measure all the variables that are associated with treatment and outcome, then within each stratum of the population where everybody have equal value of X, then it's like the treatment is randomized, and I can estimate mean of Y1 and mean of Y0 as if it's a randomized clinical trial, and then I just combine the stratum-specific causal effects. This is a strong assumption because it's not empirically verifiable, as it involves something that is unknown. What if there is some confounder that is not measured? So in fact, the unmeasured confounder has the the fear of presence of unmeasured confounders has been at the center of much skepticism about observational studies. People often look at a result from an observational study and worry that there might be some bias due to a hidden confounder. So in this talk, I'm going to use letter U to denote a unmeasured confounding, such as patient's health-seeking behavior or other type of variables. And because if you control for X, I can just look into a stratum of the population. Hereafter, all the arguments that I make are going to be implicitly conditional on all the measured covariates X. And so I'm just going to suppress the notation of X and just focus on A, U, and Y. To control for unmeasured confounding, in the literature, the most commonly used method is the instrumental variable method. It is very powerful because it provides some additional information that we can leverage to detect and control for unmeasured confounding bias. However, it requires a stringent assumption of randomization, which barely happen in electronic health records data or generally the Sentinel setting. A hidden treasure in EHR data and claims data is a new type of variable called negative control variables. And the idea is that in EHR data, in addition to the treatment and outcome of primary interest, there are also a lot of secondary treatments and a lot of other treatments and other outcomes that are secondary, and those treatment and outcomes can be leveraged to reflect the underlying patient health status or health-seeking behavior, and we call them negative control variables. So now let me formally introduce what is negative control variables. There are actually two types of negative control variables, which might be slightly, so the concept is potentially different than what you might see from other literature, where people might say, okay, a pair of treatment, a drug outcome pair that I know a priori that don't have any causal relationship are considered a negative control. That's a different stream of methodology, but here we're gonna define two versions of negative control. One is negative control exposure, and the other is negative control outcome. So here's an example, and the scientific question is, does stress during pregnancy affect baby's birth weight? Suppose I want to conduct a study and I want to estimate the effect of mother stress on baby's birth weight, which is A and Y. And suppose I measured a bunch of variables that I worry might be confounders, but I'm still concerned that there might be some hidden bias due to incomplete list of confounders. There might be some unmeasured confounding. What can I do to validate my result? Is there something that I can measure to check whether there is hidden bias due to unmeasured confounding? One way to do that is to measure father stress. The reason is because during pregnancy, the father do not carry the baby. So the only way that father stress can impact baby's birth weight is through impacting mother stress. So imagine if I run exactly the same analysis that I planned, but instead of looking at the causal effect of mother stress on baby's birth weight, I estimate the effect of father stress on baby's birth weight. What do I expect to see? I know that if I control for mother stress, there shouldn't be any causal impact or direct pathway left from father stress to baby's birth weight. So I expect to see 0. And if I don't see 0, if I see a significant non-zero association between father stress and baby's birth weight, then that must be due to some hidden pathway that created spurious association between father stress and baby's birth weight. For example, there could be some family level factors that's associated with all of father stress, mother stress, and baby's birth weight. In this example, father stress has been called a negative control exposure, and we're going to use letter Z to denote negative control exposure, or short for NCE. So formally, Z is a negative control exposure if it satisfies two conditions. One is that, very importantly, the negative control exposure does not have a causal effect on the outcome, the primary outcome of interest. And at the same time, it is associated with the outcome only through the unmeasured confounder. Or more specifically, if I control for the treatment, then the only way that Z can be associated with Y is through a hidden pathway of ZUY. Now, the fact that Z does not causally affect Y is going to be the key knowledge that I'm going to use to detect bias due to unmeasured confounding. Here's another example. The question is, does flu shot prevent 50% of death in the elderly? So decades ago, people have started to use claims data to evaluate flu vaccine effectiveness. And here's one study that looked into, among the elderly, what is the effect of flu shot on mortality during the flu season. And the study actually found that there is 50% reduction in risk of all-cause mortality during winter, which is too good to be true. If that's the case, everybody should take the flu shot. So there is, of course, concern about unmeasured confounding, for example, health-seeking behavior. In fact, in the vaccine effectiveness literature, a very commonly seen bias is called healthy user bias, which says, if you're someone like me who really care about my health, then you are going to take flu shot every year. And at the same time, you're going to have a healthy diet, healthy behavior, so you're less likely to have mortality. So if we compare people who are vaccinated, where the vaccinated group contain more of people like me, to the people who are not vaccinated, then it's really unfair to compare their mortality rate. So how do we deal with that? What this study group did is they went back and measured another type of outcome, which is mortality before the flu season. And there are two reasons to that. One is, before the flu season, there's no flu virus circulating. So there's no way that flu shot can protect me from mortality before the flu season if there's no flu virus. A second reason is that typically there is mortality before flu season, and then followed by taking the flu shot kind of, after, that time point. So flu shot typically happens after this outcome measured, the time when this outcome is measured. And because flu shot happens in the future, we know that the future does not cause the past. So A is something happens in the future, and mortality before the flu season happens in the past. So we expect to see no causal effect from flu shot to mortality before flu season. Now, what they found is that, in fact, there is an even larger amount of reduction in risk of all-cause mortality before the flu season, which indicate that there must be some hidden pathway that drives such a spurious association, for example, due to health-seeking behavior. In that example, the mortality before flu season has been called a negative control outcome, and we're going to use letter W to denote a negative control outcome, or NCO. So formally, W is a negative control outcome if, number one, is not causally affected by the treatment, and number two, it's associated with either the negative control exposure or the exposure of primary interest only through the unmeasured confounder. So basically, if I see any association between A and W, then it must be because there is a hidden pathway. So that is the key knowledge we use to detect confounding bias. To summarize, there are two types of negative controls. One is NCE, that does not cause the outcome. The other is NCO, that is not caused by the treatment. And both of them are in some way associated with the unmeasured confounders that you're worried about. Besides this figure that I just showed, where there are quite a bunch of arrows, in fact, you don't have to have an arrow between A and Z, and you don't have to have an arrow between W and Y. And also, Z does not need to be caused by you. It can be that Z goes to you, and the direction in the arrow between U and W can also be switched. So here's a list of all examples that encode the negative control assumptions, and where they're organized by examples of valid negative control exposure and negative control outcome. What I wanted to draw your attention to is that, number one, the negative control exposure doesn't have to be pre-treatment. It can be either a pre-treatment variable or a post-treatment variable. And in addition, the instrumental variable is actually a special case of a negative control exposure variable. And moreover, if you have an invalid instrumental variable that happens to be not randomized and associated with the underlying unmeasured confounder, it's still a valid negative control exposure, and you can still use it to control for unmeasured confounding. So that's a big kind of opportunity for us to leverage those type of variables. The negative controls, as you can see, are widely available. For example, in air pollution studies, people use the fact that the future does not cause the past to leverage the entire time series data to estimate the effect of air pollution on patients' health, adjusting for unmeasured confounder. In genetic research, control genes have been used to control for batch effect due to sequencing using different machines or at least different location. In the drug safety and in drug or vaccine comparative effectiveness and safety studies, people have been using secondary treatments or secondary outcomes that are widely available in EHR data as negative control variables. And more importantly, if you have a bunch of such treatment or an outcome, note that in EHR data, a lot of variables are binary. You can actually combine those multiple binary variables into a categorical variable with multiple categories. The more categories you have, the more information you have to uncover the variation due to the underlying unmeasured confounder. So as you can see, there's a big potential of leveraging the variables that we didn't previously look into to control for unmeasured confounder. So we did a little literature review and looked into the literature to see what are existing methods and application leveraging negative control variables. And we found two things. One is that when people use negative controls in application or in practice, it's being focused on bias detection. So basically, if you look into the literature, you will find that there's a section called falsification tests or falsification outcome, where there's a list of ICD-9 codes or ICD-10 codes that people use to identify negative control variables. And then they check whether there is bias to validate the validity of the conclusion of that study. However, if there is truly some bias detected, people don't know what to do next. Now, in terms of the methodology development, a few years ago, the methods have been really limited to bias reduction, and only a few methods considered bias correction. And a lot of those methods require very stringent assumptions about the underlying data generating mechanism. We, in the past few years, developed a sequence of methods that can identify the causal effect, adjusting for unmeasured confounding using a pair of negative controls without requiring any modeling assumptions, which is very flexible, and it can be applied to a range of settings. So I'm going to provide some intuition behind how we can identify the causal effect when we have one negative control outcome or just one negative control exposure, and why and when can we use a pair of negative controls called the double negative control. So let's go back to the flu shot example, where we want to look at the effect of flu shot on mortality, which is A and Y. Now, when there is a unmeasured confounding due to something like health-seeking behavior, if I look at the association between A and Y, it has two components. One is the direct causal effect from A to Y. The other is the spurious association due to this unmeasured confounding. And this amount of spurious association is in fact a product between the association between UA and the association between UY. I'm gonna denote them as gamma AU, that's the UA association, and beta UY, that's the UY association. So essentially, you can trust me that under certain linear additive model, the confounding bias is exactly this amount, the product between gamma AU and beta UY. So if I can identify what is this quantity, then I can just remove the amount of unmeasured confounding bias and get back to the actual causal effect. Of course, if I directly regress Y on A without adjusting for U, that would be the combination of the causal effect plus the amount of confounding bias, and we don't want that. So how do we do that? Suppose I can measure mortality before flu season as my negative control outcome. Then, of course, this variable is also associated with the U, the unmeasured confounder, which is health-seeking behavior. And let's look at the association between A and W. We know that A does not have a direct effect on W. So if I look at the association between A and W, there is only one component, which is the AUW pathway. And that is the product between gamma AU and beta UW. So if you compare the confounding bias, the black times blue, versus the association between A and W, which is this exact same arrow, black arrow, times another blue arrow. Suppose I am able to assume that the strengths of association between health-seeking behavior and mortality during flu season or the mortality before flu season, if those two pair of associations are of equal strengths, which means beta uy and beta uw are the same, then I'm done, right? I can just look at the association between A and W, and that recovers exactly the amount of confounding bias. So if that is something that you're willing to assume, then what you can do is run two regressions. One is regression the outcome on treatment. The other is to regress the negative control outcome on treatment. And then just take the difference between those two coefficients that will recover the causal effect. A special case of this is actually the classical method called the difference in differences, where you run two regression where the negative control outcome is the baseline outcome. And you look at the difference between the association of treatment and outcome versus the association between the treatment and baseline outcome to adjust for unmeasured confounding. Similarly, there's an idea from the negative control exposure. So again, I want to uncover the product between gamma AU and beta UY, but now I'm gonna highlight gamma AU as red. Now, if I look at the association between Z and Y, it is the product between UZ association and UY association. And if I'm willing to assume that the two red arrows have equal strengths of association, then the ZY association recovers the amount of confounding bias. So the solution would be, under this assumption, you just regress the outcome on A and Z, and then take the difference in the coefficients of A and Z. A special case is methods developed in air pollution studies, where people find that if you control for the negative control exposure, it can attenuate the amount of unmeasured confounding bias. But what we found is that in addition to attenuation, you can actually control for unmeasured confounding bias using a smarter method. Now, what if the red arrows are not of equal strength and the blue arrows are also not of equal strength? Then in this situation, the AW association, which is gamma AU times beta UW, it still reflects that if it's non-zero, it still reflects that there must be some confounding bias, but it's up to a scale. So the scale relates the difference between UY association and UW association. Of course, we can't really identify those two quantities because it involves a unmeasured confounder, something we don't get to measure, a latent factor. But although we can't identify those two quantities, we can actually identify the ratio, that scalar. So how do we do that? If you look into ZY association and ZW association, if I take the ratio between ZY association and ZW association, it's gonna be the product of the red arrow and this shorter blue arrow against the red arrow and the longer blue arrow. And the gamma ZU part cancels out. So the ratio between ZY and ZW associations is exactly equal to the ratio of UY and UW association. So from here, you can see that the negative control exposure and negative control outcome actually play very different roles in terms of identifying the causal effect and controlling for unmeasured confounder. In particular, the negative control outcome, it recovers the amount of unmeasured confounding bias, but up to a scale. And the negative control exposure serves as an instrument that recovers exactly that scale. And so based on this idea, we can control for unmeasured confounding without making stringent assumption that the two red arrows are equal or the two blue arrows are equal. And we call this method double negative control method. So more specifically, I'm gonna give you a more formal example in the case of linear additive models, which will allow me to generalize to the idea of a non-parametric identification that doesn't really require any modeling assumption, and it applies to continuous outcome, binary outcome, or count outcome, any type of outcomes. So for simplicity, let's start from a linear additive model. So suppose the outcome is related to treatment, NCE, and unmeasured confounder through a additive model. Note that in this model, there's no Z. Why is that? It's because if I'm able to control for the unmeasured confounder, then Z shouldn't have any causal effect on the outcome. So this model doesn't involve Z. Similarly, the negative control outcome is related to AZU as gamma 0 plus gamma U times U. There's no A and Z because AZ does not directly cause the negative control outcome. From the first model, you can see that beta A is exactly what I want. This is the amount of causal effect due to the fact that this is just a linear additive model, the coefficient of treatment is the ATE. But I can't directly run the first model to adjust for unmeasured confounder. So what do? You can see that from the second model, I know how to replace U. I can replace U with the negative control outcome model, and you can show that, in fact, the outcome model given A and Z is equal to beta 0 star, which is not beta 0, but beta A times A, the same beta A, plus beta U star times a model for W given A and Z. So this motivates the idea that if I fit a model where I regress negative control outcome on treatment and NCE, then predict a W hat, then I can treat W hat as the unmeasured confounder and just run an outcome regression as if the way I plan to do if I were able to measure U. But instead of using U, I replace it with W hat. So this idea can be extended to a non-parametric identification of the causal effect, where note that the ATE is just mean potential outcome difference, right? Mean of y1 minus mean of y0. So all I need to do is to identify the mean of potential outcome. And it turns out to be identified by mean of a function called h, and it has two arguments, the treatment and the NCO, the negative control outcome, where this function is called a outcome confounding bridge function, and it satisfies that the mean of the actual outcome given A and Z is equal to mean of this H function given A and Z. In this example above, the H function is exactly equal to beta 0 star plus beta AA plus beta U star times W. So this gives us a conclusion that if I am able to find and identify this confounding bridge function, then I will be able to identify the causal effect. The key assumption required here for this non-parametric identification to work is that you need to have good negative controls. The negative controls must be associated with the underlying unmeasured confounder, and it needs to carry sufficient information. What I mean by sufficient information is that suppose Z and W and U are all discrete, they're a categorical variable. Then the number of categories of Z and W need to be either equal or larger than the number of categories in U, which intuitively makes sense because I need sufficient amount of variation in Z and W to recover the bias due to the variation in U. So in practice, if you're willing to assume a linear model, not even need to be additive, there can be interaction between variables, then you can just run something called a two-stage least square, where in the first stage, you regress the negative control outcome on treatment and negative control exposure. You get a fitted value of W hat. You treat it as if this is just the unmeasured confounder U. It's a proxy of U, and then run the outcome regression, adjusting for the proxy of U. The nice thing is that two-stage least squares has already been implemented in off-the-shelf software packages. So there's packages in SAS, in Stata, and also in R. For example, in R, all you need to do is just to run one line function where I specify what's my outcome model and what's the model for the negative control outcome. Of course, here you can additionally control for measured confounders X. So that's pretty convenient. But the next question is, how do I know there's a negative control variable? How can I find a candidate negative control variable? Typically, the ideal case is that you want to work with a scientific investigator who have a good understanding of the scientific problem and the underlying unmeasured confounder, as well as candidate variables. And then you can check based on your subject matter knowledge to see whether certain variable satisfies the NCE and NCO assumptions. However, with hundreds of thousands of variables from EHR data, of course, we want to find a data-driven method that can scan through all the variables in EHR to identify candidate negative controls that satisfies the negative control assumptions. So because of that, we developed an algorithm called Data-Driven Automated Negative Control Estimation, or DANCE. I personally really like this name because it's quite a nice name. And this DANCE algorithm has two steps. In the first step, you will run some statistical tests that will allow you to identify multiple triplets of negative control variables. Each triplet of negative control variables contains 3 negative controls, and for each pair, every 2 out of 3 will give you an estimated ATE. So in the second step, what you do is you're going to use a method that can aggregate all the ATEs from all pairs of negative controls. The limitation of this method is that it can only detect a special type of negative control variable, which is displayed in this figure. So in this figure, the NCE and NCO must satisfy that there's no arrow between Z and A, and there's no arrow between Y and W. So recall that in previous figures, we might allow for arrow between ZA and YW, but our method can only detect this special type of negative controls. Why is that? It's because of how this method works. The rationale behind this statistical test for identifying negative control is the following. If you look at how Z is related to A and Y, or how W is associated with A and Y, the only way under no arrow between A and Z that Z can be associated with A and Y has to go through U. So the only pathway from ZW to AY must go to this one single factor, that unmeasured confounder U. As a result, if you look at the association between those four variables, which will give you a 2x2 matrix, and because they all are related to each other through U, you will see that this 2x2 matrix is rank deficient in the sense that the rank is smaller than its dimension. In fact, this matrix would be rank equal to 1. And such a rank constraint can be determined using some statistical tests. And that is why we're only able to detect this special type of NC negative control variables. If there's a additional pathway, for example, Z can go to Y through A, then we won't have rank deficient condition. So that is why this method only works for this special type of negative control variables. So here's some simulation result that displays the performance of the Downs algorithm in terms of searching for negative control variables and then followed by estimating the causal effect. You can see that, so each curve here corresponds to a different sample size. And you can see that as sample size increases from 10 to 1,000, we can have AUC ranging from 70% to 100%, which means the method works really well, even for relatively modest sample size. On the other panel, on the right panel, again, the x-axis is increasing sample size and the y-axis is proportional bias. The red one is the raw estimated causal effect, which is without any confounding adjustment. The blue one is I just pick some random pairs of variables available from EHR data, pretend that they're negative controls. For example, some secondary treatment and secondary outcome, and then use the negative control method to estimate the causal effect. Whereas the green ones, the green dashed lines, are the bias and confidence interval for the negative control pairs that are detected from the Downs algorithm. And you can see that the bias from the green ones are pretty low, whereas if you just use naive method, it can give you a really wrong conclusion for the causal effect. So for a very long time, we have been thinking that if you want a negative control exposure is an exposure, and the negative control outcome is an outcome. But then recently we realized that actually NCE and NCO does not have to be outcome or treatment. And they're actually wider than that, more general than that. So we call it proximal causal inference. And it's driven by a question of, are two cheap and noisy measures better than one expensive and accurate measure of a confounder? So the idea is that the no unmeasured confounding assumption, it depends on the investigator's ability to accurately measure a confounder, which might not be true in the EHR setting because there's not even a concept of a confounder. The EHR data is not designed to answer a particular research question. So all the variables, they're just passively measured. And you can't really say, I want to measure, for example, people's diet or health behavior. So essentially, the most one can hope for is that covariates measures are at best proxies of the true underlying confounding mechanism. So it's really hard to eliminate measurement error. However, do we really want to spend so much effort, resources, time, and money to measure accurately a confounder? The answer is maybe not, because it's easier to get the right kind of measurement error than the right kind of confounder. So as long as if we can acknowledge that covariates are just imperfect proxies of confounders, and then we can find some proxies that satisfy the negative control assumption, then we don't really need to assume no unmeasured confounding. In fact, we can allow the no unmeasured confounding assumption to be violated because in fact, it can easily be violated due to measurement error in the measured covariates even. So here's an example to illustrate what I just said. This is a study that evaluates the adverse effect of a newly labeled zoster vaccine on an outcome adverse event such as acute MI. When this study was designed, the investigator wanted to measure, the traditional type of confounder that we typically adjust for, such as age and gender, but also proxies for health-seeking behavior. It's not really easy to just measure health-seeking behavior because it's kind of multidimensional, but you can find proxies that reflects a patient's health-seeking behavior. For example, does the patient have dermatology visit, or does the patient have hypertension at baseline? So in this example, dermatology visit has a direct causal impact on whether the patient takes zoster vaccine, and it is associated with health-seeking behavior and then associated with acute MI. On the other hand, hypertension at baseline might have a causal effect on acute MI post-vaccination, and is also associated with zoster vaccine through health-seeking behavior. So essentially, C, X, and W in this design of the study can all be viewed as confounders, which are associated with both the treatment and the outcome. So the study design, the statistical analysis plan that was originally generated was to run a regression where I regress the outcome on zoster vaccine, controlling for all of those variables that includes proxy of health-seeking behavior and age, gender, or other type of variables. Now let's think about how it works. First of all, if I adjust for age and gender, then I break the pathway that gives a spurious association between A and Y. Now, second, if I adjust for dermatology visit, I break the pathway between A and U, the zoster vaccine and health-seeking behavior. So that further remove the unmeasured confounder due to the pathway of A, Z, U, Y, right? That creates a spurious association between A and Y. Similarly, there's still one pathway, the blue one, A, U, W, Y. And if I control for hypertension, I break the pathway so that there's no more pathway from U to W to Y. Now I have already adjusted for all the confounders that I measured, but you can see that there is still one pathway that is not excluded, which is the pathway of A, U, and Y. That is direct pathway, not through Z and not through W. So what that means is, even if you're able to measure proxies of the unmeasured confounding, if you didn't adjust for them in a better way, you might still be subject to health-seeking behavior. So what we propose is an alternative method. Instead of the previous statistical analysis plan that controls directly for those measured covariates through regression adjustment, we propose to break those variables into 3 buckets. The first bucket is X, which causally impacts the treatment and causally impacts the outcome. That's the typical definition of a confounder. And then the dermatology visit, we view it as something called a treatment-inducing confounding proxy, which is directly related to the treatment, but associated with the outcome indirectly through the unmeasured confounder. We call it Z. As you can see, this letter Z, the dermatology visit, is actually a negative control exposure. It satisfies the negative control exposure assumption. And similarly, we call W, hypertension, the third bucket, which is outcome-inducing confounding proxy. And as you can see, it is not causally impacted by the treatment, and it has an arrow from W to Y, and it's associated with the treatment indirectly through the unmeasured confounder U. So instead of directly adjusting for those 3 type of variables, we're going to split them into 3 buckets and leverage the double negative control method, which allows us to remove confounding even due to this hidden pathway that was not previously adjusted. So to make a little comparison between the classical causal inference and the proximal causal inference, here's the idea. In classical causal inference, we're going to adjust for all 3 types of variables as confounders, measure covariates. And we have a standard G formula that says, okay, if I run an outcome regression model, I have the model and then I marginalize over the target population, that gives me the mean of the potential outcome. And then that's the standard G formula, and we can estimate the causal effect using G computation. However, it might fail, as we just illustrated, when there's unmeasured confounding and that pathway that you can't really get to control for. Instead, using exactly the same amount of data, we can split them into 3 buckets and use the double negative control method. And here, recall that we have the confounding bridge function or the outcome bridge function H. So instead of using the standard G formula, we can use the proximal G formula, where again, the mean of potential outcome is still the mean that's integrated over the distribution of the target population. And we can estimate the causal effect. Instead of using G computation, we can use the proximal G computation or 2-stage least squares. In fact, if there is no unmeasured confounding, then the G formula from the proximal causal inference, it reduces back to the classical causal inference scenario. So there's a strong connection between the classical method and the proximal causal inference method. And the proximal causal inference would be able to allow us to adjust for unmeasured confounder just by splitting the confounder that you previously designed to adjust for into 3 buckets. So here's the illustration of how we used it in the actual, in a real analysis, a real application. So we're going to look at a particular procedure called the right heart catheterization, or RHC. So RHC has been performed to measure the blood flow and pressure in the heart. And the physicians believe that such measurement can guide therapy and decision to lead to better outcome for patients in the ICU. And because of such a strong belief, it's unethical to conduct a clinical trial to evaluate the effect of RHC on patients' survival. And because of that, in 1996, Connors and others run a study called the SUPPORT study, which is the study to understand prognosis and preferences for outcomes and risks of treatments. So this study evaluated the effectiveness of RHC among adults admitted to the ICU. And in this study, there are about 2,000 patients that are given RHC, whereas about 3,500 that are managed without RHC. So what did this study found? This study found that RHC actually is harmful. It's associated with reduced survival. So this is a very controversial result. It's opposite to physicians' belief. And why is that? One particular reason is that there might be some confounders that's not adjusted. For example, patients who are managed with RHC might be a lot sicker than patients who are not given RHC. And there might be factors that drive such decision, which are associated with survival, but we didn't measure them. So potential unmeasured confounding is one particular reason for such a controversial result. And because of such an influential study, this dataset has been analyzed by many researchers in causal inference. However, a lot of the methods have been relying on the no unmeasured confounding assumption. So in this exercise, what we're going to do is we will first identify proxies and then leverage the proximal causal inference method to control for unmeasured confounding. So here's the background. In the SUPPORT study, the investigator collected 72 covariates, which measures patients' demographics, comorbidity, vital signs, functional status, as well as physiological status. And for physiological status, it's being measured from a blood test during the first 24 hours in the ICU. We know that a lab test cannot be extremely exact, and it's just a partial story or a mismeasured version of the true underlying physiological status. So that gives us a list of candidate proxy variables that we're going to search for to see whether some of them can serve as a negative control or an actual proxy. So what we did is we applied our dense algorithm to identify valid proxies. And we found that the most frequently selected pair is pH and SOD. So here pH stands for serum pH level, and SOD stands for serum sodium level. And again, the other 60-something measure covariates are gonna be put in the third bucket of X. So we're going to evaluate the effect of RHC on survival time in days, which is a continuous outcome. So we will assume a linear additive model just for simplicity. And in terms of estimation, we run the proximal two-stage least squares. And to adjust for the other 60-something covariates X, we used inverse probability weighting. So here's what we found. Recall that the most frequent pair that we identified as valid negative controls are pH and SOD. And in fact, if you look at this figure, they're symmetric. So we looked at what's the result if I set pH as W and SOD as Z, or the alternative. And what we found is that for both pair of negative controls, although the point estimate is still negative, which says running RHC is associated with a lower amount of survival time or reduced survival time. However, the confidence interval, it actually covers 0, which means there's not a significant association between RHC and survival time. Now, we also run an analysis where we aggregate all the ATE using all detected negative control pairs, and we found similar conclusions. Whereas if you just run a naive regression adjustment where you regress survival time in days on the treatment and all the measured covariates, you will see that RHC is harmful, which is the previous controversial result. One thing that's really interesting is that we mentioned Z and W in this special case are actually exchangeable. So if the graph is true, which means if our negative control identification method actually worked and found a correct graph, then we expect to see that when I switch the role of Z and W, the conclusion should be very similar. And that's exactly what we see. Both the point estimates and the confidence intervals are very similar to each other, which verifies that our density algorithm correctly specified or identified this causal graph and found the valid negative controls. So to summarize, I'd like to say that in the Sentinel setting with thousands of variables available from EHR and claims data, we should leverage the hidden treasure, which is negative controls and proxies, to adjust for hidden confounding bias. And the nice thing about those methods is that you can directly use off-the-shelf software packages. And we also have developed a data-driven pipeline from searching for negative control variable from within the EHR data to adjusting for unmeasured confounding using the detected negative control variables. And lastly, I'd like to say that our team have developed negative control methods and proximal causal inference methods for many, many different scenarios. So we have conducted a review of existing literature on use of negative controls. We provided non-parametric identification of the causal effect, which does not rely on modeling assumptions. We looked into the setting where your outcome, treatment, and negative controls are binary. How do you estimate the causal effect? And we introduced the outcome confounding bridge and also treatment confounding bridge, which allows you to develop a doubly robust estimator that does not require correct specification of either the outcome or treatment model. We also then introduced the proximal causal inference framework and then extended it to longitudinal data setting. We also developed the proximal causal inference method for the survival analysis setting. We also developed this method in the panel data setting, as well as for mediation analysis. So there's a stream of methods that have been developed that leverage such rich sets of potential negative controls and proxies available from EHR and claims data. And I think that concludes my introduction for today. Thank you for your attention.
Thank you, Dr. Shi. That was a terrific presentation. I really appreciate you walking us through step by step of this complex procedure. I think a lot of us have benefited from this presentation quite a bit. So again, as a reminder, this floor is now open for questions and answer session. You can type your questions in the box. Your lines are muted. So there are a few questions that I can probably start with for Dr. Shi. So one of the first questions by Frank Tran is related to the concept that the method assumes that there is one negative control, the control outcome or exposure is identifying, relying on this single unmeasured confounder. What to do when you have more than one, and they may attempt to get at different unmeasured confounders. So any thoughts on that?
That's a very good question. A key kind of limitation is that you need to have in mind what is the unmeasured confounder that you want to control for example, health-seeking behavior, to search for negative controls, because you require the negative controls to be associated with the unmeasured confounder. If I don't know who the unmeasured confounder is, how can I find such a negative control? The only, the only exception is the air pollution study or time series data setting, where for any type of unmeasured confounder, as long as it is associated with treatment and outcome, then you can just use future or past treatment and outcome as negative control variable. So this is the only exception where you don't really need to know who is my unmeasured confounder. Now, suppose I have different types of unmeasured confounder. We didn't develop such a specific method, but I believe you could use different pairs of negative controls that each target a different type of unmeasured confounder to remove bias specific to that unmeasured confounder. Of course, there might be some other assumptions. For example, if I'm willing to assume a parametric model that relates the different type of unmeasured confounder and the outcome, then I would be able to leverage all the different negative controls to remove bias. That's a really good question. Thank you.
Great. Thank you for answering that. There are other questions that I can quickly summarize. So Yan Lee asks that your specific question about your ADDIC study, you assume that serum sodium and serum pH are linked through unmeasured confounders, which confounds the relationship between ADDIC and mortality. What if there are other direct or indirect link between the two?
Okay, so let me go to that figure 1 second. Linked through unmeasured confounder. What if there are other direct or indirect links through other covariates, through other variables between these two? So if there are other variables that drive, A, Z, so Z, A, Y, W, it is still okay as long as they're measured. You can adjust for them. But if there are unmeasured confounders that relates to Z and W, if that unmeasured confounder is associated with all of the 4 variables, Z, A, Y, W, then all of them can be controlled by Z and W as long as the number of levels are satisfied. But in this case, they are continuous. So there's no such an issue of insufficient information. So that also relates to Rishi's question. If the different type of confounders are associated with all different type of U, if I have U1 and U2, and they're both associated with my selected Z and W, then I can still treat them as a combined set of U. So this U variable doesn't have to be, one dimension. It can be a vector of multiple unmeasured confounders. However, if there are, some U1 or U2 that's not associated with this pair of Z and W, but other pairs of Z and W, then you might, for that case, you might need to use a different set of methods.
Okay, thank you. So another question recently came in. David Carell asks, with the dance approach, is there a possibility for adjusting too much or over adjustment? Have you thought about that?
I see. That's a really good question. So that's why when we think about once I select, multiple triplets of negative controls, what do I do next? And we thought one way is you pick the most frequently selected pairs and use that as double negative control, or you average over all the detected pairs. But if you aggregate all the detected pairs, it could bring in, over controlling situation. Yeah. So if that's the worry, I would recommend just use the most frequently identified pair. And you know what they are, so you can combine that with even with your subject matter knowledge to see, okay, does this algorithm, match with my expectation?
That makes sense. Thank you. So I have actually a follow-up question about the dance algorithm. So it seemed like that there is some kind of pre-selection going on there. So you had, for your ADDIC study, for example, you had 72 variables measured, but you only sort of considered 10 as candidate variables. So right. What's the thought behind selecting those, and how do you go about this?
Right. So we looked at the variables, and we thought the other variables are likely the first bucket where they have a causal effect on A and Y. But the physiological status, it really isn't a perfect matter. It's just some lab test. So we would think these are candidate proxies. In other type of applications, you could actually just run through all the covariates, and the algorithm would be able to, find just the set of variables that satisfies this graph. So basically, if I were to run this algorithm, I would still highly likely identify variables from the 10 proxies.
I see. Okay. And is there any computational considerations when you run so many variables at the same time?
That's a very good comment. So it involves, for every single pair, it's one statistical test, at least one. So, and there are multiple combination of different triplets and different pairs. So the more covariates you have, the longer it takes for the algorithm to run. For as low as 72 covariates, it didn't take me too long to run the algorithm. But if you have thousands of variables, it does potentially take a long time. We haven't developed methods that improve the computation efficiency, but that should definitely be something we explore in the future. Yeah, that's a good point.
See. Okay, thank you. There's one more question that came in, which asks if you are assuming just the additive model, or are the interactions possible through your method?
Yes. So let me go. Maybe 1 second. So here might be a good place to talk about. The first 2 bullet points is just an illustration under a linear additive model. You can have any type of model, nonlinear or linear. You can have any type of interaction between AU, AZ, or W also in the W model. So the final conclusion is that the causal effect can be non-parametric identified. So it doesn't really rely on any restriction about no interaction or linear model. This is just for illustration purpose.
Okay, thank you for answering that. That makes sense. I guess most of the questions were related to proximal method, which is not surprising because that's really exciting for people to learn about. But when you were presenting something, the basic chart, that very nice table that you had, and you mentioned something that really caught my eye and made me think about how we may have been missing the opportunity to use IVs, imperfectly measured IVs, as potential negative control exposures. And so my question to you is that, is this something that has ever been tried or shown to work before, or is it purely theoretical at this point?
It works. So everything that satisfies the graph in this table, if you have an invalid IV that is associated with the unmeasured confounder, as long as you can find a negative control outcome, then you can use the pair of invalid IV and the negative control outcome to remove confounding bias. Yeah.
And so in that case, do you need still the IV to kind of meet this assumption of strong association with the treatment, or can you relax that a bit as well?
Right, you don't need that assumption. That's
you don't
a good
need
point.
That, right?
So,
it's just another variable at that point. Yeah. Okay.
Right. Yeah. The only assumption you do need to satisfy is the exclusion criteria. So the exclusion restriction, which is also required by the NCE assumption. Right. So both require that. Yeah.
That makes sense. Okay, excellent. And there are a couple of questions related to whether slides will be available, whether this is recorded. So yes, this is recorded. The slides will be available on sentinelinitiative.org, which should be posted in a couple of days. So I think, so there was one more question that came in. In slide 10, you mentioned that the method can combine multiple binary negative control variables or 2 categorical variables. How does that work? Can you talk more about that?
Yeah. So if you have binary variables, which is highly likely from EHR data, and suppose I find multiple variables that are valid negative control exposures and multiple binary variables that are negative control outcome, then I can let's say I find 2 binary variables that are NCEs, then I can create a categorical variable of 4 categories, which is the combination of the 2 categories of each of the binary variable. So that means I have more categories, and I would be able to identify more bias from a unmeasured confounder of higher level of categories. So the more binary variable you have, the categorical that you combine into would have more level, and that's better. Yeah.
Okay, that's excellent. Thank you again for taking the time today to respond to all our questions with such great detail and clarity. I, for one, really appreciated this presentation, and I'm sure a lot of attendees felt the same way. So with this, join me in thanking Dr. Shi today again. And as a reminder, this is recorded and will be made available on our webpage. And you can also find details for registration links for future seminars in the series on our same website. So this concludes today's session. I will see you again next time. And again, thank you, Dr. Shi, for presenting such eloquently on such a complex topic.
Thank you very much, everyone. Bye.